Hello and welcome to Linear Models with Matrices. In this first module, we'll be talking about simple linear regression, which will be review for most of you, but I want to use this as an opportunity to get back in the swing of things and think carefully about what we're up to here when we're doing statistics. So what makes an analysis statistical? We can do all sorts of types of analyses, but I think we mean something different when we talk about a statistical analysis. And I tend to think of statistics as a framework for making reasoned judgments about quantitative evidence. So I've broken this down to sort of a 5-step process here, and I don't mean to be overly formulaic, but I want to sort of lay out some of the things we think about when we're doing a statistical analysis. So the first thing you probably think about or should be thinking about is formulating a question that you'd like to answer. Once you have your question, you design a study and collect data. And the third step is kind of crucial for distinguishing an analysis from a statistical analysis, is that in a statistical analysis, we choose a statistical model for the data. And we'll say more about what that means in a minute here. Once we picked our model and we have our data, we can estimate the model or model parameters from the data. And then at the end of the day, we have to look at all the evidence and make a judgment about the answer to our question. And that's taking into account, all of the things that you did prior to getting to this last step. What is your question? Are the data relevant to the question you're trying to answer? What's good, what's bad about the statistical model that you picked? How accurate are your estimates of parameters in the model? And you have to use all of these things and come up with a judgment. So this course is about linear models, which is one set of types of statistical models. Linear models are designed to help us answer questions like, is the response, which is also known as the dependent variable y, related to a covariate, which is also known as an independent variable or predictor or feature, x? Or more often, we have a question like, is the response y related to x after controlling for another variable z? Okay, so what is a statistical model? I'm going to define it here to be a family of probability distributions encoding assumptions about how data were generated. And we'll quickly get into some examples of this, but a couple things to note about this definition. There's some notion of probability associated with a statistical model. We represent our uncertainty about what the data are going to be with probability distributions. We have a family of probability distributions, which means we're not saying it's this one particular probability distributions. There could be a range of them that we could have. And another important aspect is that in a statistical model, we make certain assumptions about how the data were generated. And statistical modeling is really, really, really all about deciding what you want to assume to be true and what you want to learn from the data. So let's look at what we call the simple linear model. Our notation for the response is going to be y, and we'll have n responses. So we'll label them y1 up to yn. The covariate we'll call x, and there's one covariate for each response. And so we'll label those also x1, x2, up to xn. And then our model for the data, little yi, we'll write as capital Yi equals b0 plus b1 xi plus epsilon I. Now, as I said a minute ago, one reason for picking such a model is we're interested in answering the question, is y related to x? All right, so what do all these symbols mean? First of all, one of the conventions, notational conventions we'll be using in this course is that lowercase letters refer to non-random quantities and uppercase letters refer to random variables. Now, we'll sometimes break this convention, but we'll try to be clear about when we're breaking it and when we're not. So in the model, we have capital YI on the left side, so that's a clue that this is going to be a random variable. On the right side, we start with B0 plus B1 xi. So B0 and B1 are lowercase letters, so according to our convention, these are just regular old numbers, but we're using a symbol for them, so that indicates that they're unknown, and we'll call these unknown numbers in a statistical model parameters. And then there's epsilon I. Now, epsilon I is going to be a random variable, and we'll denote random variables, the distribution of random variables with the random variable, then we'll do this little tilde. So when you see the little tilde, think in your mind, is distributed as. So epsilon I is distributed as normal, mean zero, variance sigma squared. The other part of this is I put the little IND over the tilde. That stands for independent. So what I mean by that is if you take the collection of random variables, epsilon 1, epsilon 2, up to epsilon n, those collection of random variables are independent. Now, in defining the distribution for epsilon I, we introduced another symbol, sigma squared, and this is the variance of the distribution for epsilon I. And this is also going to be an unknown parameter. Okay, so because if we look back at this equation, on the right side of the equation, we have non-random plus random, then the thing on the left side must be a random variable. So if you add a non-random to a random, you get a random variable. So any piece of randomness kind of makes the whole thing random, according to our definition of what a random variable is. So that makes yi a random variable. And once we say it's a random variable, then we can do some types of operations with it. So one of the operations you can do on random variables is to compute the expected value. So if you were to compute the expected value of yi, you'd get b0 plus b1 xi, and that's because we assume that the mean or the expected value of epsilon I is 0. All right, a few questions here. Does this model fit the definition of a statistical model? So let's look back at that definition. It says it's a family of probability distributions encoding assumptions about how data were generated. So it's a random variable, which means it has a probability distribution. So it does satisfy that part. It does encode some assumptions. So we'll come back to that in just a second. So I think it does fit the definition of a statistical model. How would estimating the model parameters help us answer our question? So let's look at what the question was. Is y related to x? And if we look at the expected value of yi, we see it's a linear function of x. So the expected value of y is b0 when xi is 0. That makes b0 an intercept. And the rate of change of the expected value of yi with respect to xi is b1. So b1 is a slope. That's why we call it a linear model. So one of the assumptions that's encoded here is that the way that y is related to x is this linear relationship. And so if we can estimate these two parameters, b0 and b1, we can say something about what that linear relationship is. So this goes back to my point above here, is that statistical modeling is all about deciding what you want to assume to be true and what you want to learn from the data. So in this model, we've assumed that the relationship between the expected value of the response and the covariance is a linear relationship, but we've not assumed what that particular linear relationship is, meaning we've not made any assumption about what the intercept is and what the slope is. So that's what I mean when I say modeling is all about deciding what you want to assume to be true and what you want to learn from the data. So if we can estimate these two parameters, we can say something about what that relationship is. But again, we've encoded this assumption that the relationship is linear, which it might not be. So one of the ways the assumptions could be violated is could be a nonlinear relationship between expected value of yi and xi. Another assumption that could be violated is in the distribution of these epsilons. So what do these epsilons represent? They represent the deviation between what you get to observe, the yi, and its expected value. So one of the assumptions is that those deviations come from a normal distribution, so that could be violated. Another assumption is that we assume that they're independent. So that could also be violated. There could be some correlation within the error terms. So those are just a few of the ways that the assumptions could be violated. All right, so down here we have a plot of what the model might look like. So, and the data might look like. So on the horizontal axis we have the x's, and the vertical axis we have the y's. And so each little dot on this plot represents a pair, xi and yi. So this might be x1, y1, x2, y2, x3, y3, and so on. So when we're observing the data, we just get to observe the points on the plot, and we don't get to see what the true value of this linear relationship is. So what we do in estimation is we try to learn what these model parameters are from the data. So we're using the data y1 to yn and x1 to xn to get estimates of the three parameters in our model. And those three parameters are the intercept, the slope, and the variance of the deviation from the line. So some terminology here. We'll be using these terms over and over, so let's give the definitions. An estimate is a function of the data, that being little y1 up to little yn. So these are just numbers. It will also be a function of x1 to xn as well. An estimator is the random variable version of the estimate. So this is going to be a function of the random variable version of the data. So if we look back to our equation here, we have responses. So these are like data points, things that you could write down on a piece of paper or could be stored in your computer. These are numbers. But when we have a model for the data, we represent that with a random variable. So this is a mathematical object, this capital YI, that is not a particular number that you could write down on a piece of paper. It's a probability distribution. So that's how we should think about random variables. They're not particular numbers, but they're represented by distributions. So the estimate is a function of the data, and then the corresponding estimator is you take whatever formula you used to create the estimate in terms of the little y's, and you plug in the big Y's. So let's look at an example of this. So in this example, we have data, little y1 up to little yn. And our model for these data is big Y1 up to big Yn are independent normals with mean B0 and variance sigma squared. Now the estimate that I'm going to use for the mean of this normal distribution, I'm going to call that little B0 hat. That's going to be equal to the sample average of the y's. So that's just the estimate that I'm picking. And so, for example, that would be equal to 6.37. So an estimate is a function of the yi's, which are just numbers. And so this is just a number. For the estimator, this is going to be a random variable. And the way I construct the estimator is that I take the formula for the estimate, and wherever I see the little yi, the response, I plug in the random variable version. So what we have here is a sample average of n normal random variables. And it turns out that this thing, since it's a function of random variables, yi, it also is a random variable, and it happens to have a normal distribution with expected value b0 and variance sigma squared over n. All right, so the statistical model is useful to us because it allows us to say something about how close to the true value of the parameters we expect our estimates to be. So what do I mean by that? Let's just recap our notation here. So in this example here, the true value is b0. So we can think of that as a number, but we don't know what the number is. This b0 hat is our estimate of b0. This is also a number, and we do know what this number is because it's just a function of the data that we observed. And we put a hat on it to indicate that it's an estimate of the true value b0. And then b0, big b0 hat is our estimator. Again, this is a random variable. So we have kind of all these combinations, b0, b0 hat, big b0 hat, and we haven't said what big b0 is, but that's something we'll come back to later. All right, so what is an ideal property of an estimator? What we like is that the difference between the estimator and the true value is small. A similar statement to that is I could take the difference between the estimator and the true value and square it. And so if something is small, then the square of it is small. And so if the expected value of this thing is small, then that we can think of that as a good estimator. All right, let's do some calculations here. By the way, this thing is called a mean square error. So what we're going to do is do some calculations with the mean square error and try to break this down into something that we're more comfortable with. So if I look at this formula b0 hat, this formula for the mean square error, big b0 hat minus b0 squared, we could take this and we can add and subtract the expected value of big b0 hat. So what does this quantity mean? Remember that big b0 hat is a random variable. Therefore, we can compute things like expected value and variance. So this is just the expected value of this random variable, which is just a number. And I've added and subtracted it, so I haven't changed the equation at all. Now, if I do the FOIL operation, I get this difference squared, which is this. I get twice the cross term, so that's expected value of this difference, which is here, times the expected value of this difference. Now, both of these things are not random, so they come out of the expected value, so that's why you get this here. And then the last part is expected value of this difference squared. And again, that's not random, and that's not random, so we just get that difference squared. Now, if we look at this equation, this thing is just the definition of a variance. So this becomes variance of b0 hat. If we look at this cross term, if I take the expected value of this minus this, remember that the expected value is a linear operator, so you could do, so this becomes expected value of b0 hat minus the expected value of something that's non-random, so that just comes out. And then if you stare at this term, that's non-random, and this is 0. So something times 0 turns out to be 0, and then you have this thing left. Now this thing is called the bias. So if you take the expected value of a random variable and you subtract off the thing that you're intending to estimate, which is little b0, that's called the bias, and we're squaring it. So the formula becomes mean square error equals the variance of the thing we're trying to estimate, the variance of the estimator plus the bias of the estimator squared. Now for regression, we can usually find estimators that are unbiased. So when something's unbiased, that means the bias is 0, so that goes away. So the name of the game for regression is once you have an unbiased estimator, you just want to find estimators that minimize the variance of the estimator. And it turns out that the least squares estimators minimize the variance. So you've seen least squares estimation before, but let's introduce it in terms of the notation that we're using here. So RSS is the residual sum of squares criterion. And what I'm going to use here is B0 star, B1 star. So what I want you to think about here, this is just an argument. So RSS is a function of B0 star and B1 star. And so these are just the arguments to the function. So what is a function? A function is just you take inputs and you get an output. So if I were to write f of x equals x squared, x is just the input to the function and the output is x squared. Here it's the same thing. B0 star and B1 star are just the inputs to the function. And what is that function? We sum from I equals 1 to n, the number of data points. And we do yi minus the linear function, b0 star minus b1 star xi, square it, and then add it up. So what do I mean by this? Is I can take any two values of b0 star and b1 star, I could plug them into this function, and I get a residual sum of squares for those particular values of b0 star and b1 star. For example, I could put in 1 for b0 star and 3 for b1 star. And since I know yi and xi for every I, I'll just get a number here. So the name of the game for least squares estimation is I want to find the particular b0 star and b1 star that minimize this sum of squares criterion. So this is going to be a common theme in statistics, that we're defining our estimates to be the value of inputs to a function that minimize that function. So this is least squares estimation. Okay, so we're defining the estimates to be the minimizers of this function. How do you minimize a function? You learned in calculus that one way of doing it is you take derivatives and set them to 0. So if I take the derivative, so I'm taking the partial derivative of this sum of squares, residual sum of squares criterion with respect to b0 star, and I'm also taking the partial derivative with respect to the second argument, b1 star, and I'm going to set them to 0 in order to find the minimizers of the function. So this is just what you get when you take the derivative with respect to b0 star. You get the minus 2 comes out, and then you just get this here. Here you get a minus 2, but b1 star is multiplied by xi, so xi gets multiplied here. Now if you were to, now you get these two equations, set them to 0, two equations, two unknowns, and you can solve for the minimizers. So the minimizers I'm calling b1 hat and b0 hat, and this ends up being the formula. So one of your exercises for this module is going to be to verify that this is the formula. And one thing to look out for is that there's several different equivalent ways of writing down the formula. And so you might get something that looks slightly different. That doesn't mean it's wrong, but see if you can verify and change the equation so that you can make it look like this. To introduce some new notation here, now that we have our estimates, little b0 hat and little b1 hat, we can calculate something called the fitted values. So what the fitted values are is just I take our estimates and I plug them into that linear function with xi there. So yi hat is just the estimated linear function of xi. The residual, I just take the data minus the fitted values, and we denote that with ei hat. And if we were to plug this equation into this one, we get yi minus b0 hat minus b1 hat xi. You could look at the random variable version of this. People don't normally look at this, but you could. We actually will when we study properties of variances. But one thing to note is this is not the same thing as epsilon I. Epsilon I is big yi minus the true linear function. Okay, last parameter to estimate is the variance parameter, sigma squared. If you think about the variance parameter as a measure of how much the data will vary from the true regression line, we can use the variations, the residuals, the estimated variations, to estimate this variance parameter. So a common estimate is to take the squared residuals, add them up, and divide by n minus 2. And if we're plugging in the formula for the residuals, it's just this formula here. So this is the same equation. So you might be asking, why do we do 1 over n minus 2 instead of 1 over n? And this is one of the questions that we're going to be looking at more closely later on in the semester. So I'm not giving you the answer here of why we do that, but we will study that problem in the fourth module when we talk about variance estimation. Okay, so bringing this back to our statistical framework, one of the reasons that we have a statistical model is that once we get our estimates, the little b0 hat and little b1 hat, we can look at the probability distribution of the corresponding estimators and use that to say something about the variance, mean squared error, things like that. And the way we do that is we look at the what's called the sampling distribution. So the sampling distribution is just the distribution of the estimator. So here is an expression for the estimator for B1. You'll notice that this is a slightly different formula than I gave above. And the reason is, as I said before, that there's actually several different ways of writing the estimate and the estimator for B1, and they're all equivalent. So this particular formulation is convenient for thinking about what the what distribution big B1 hat will have. So if we look at this, there's something out front that's 1 over SXX. SXX is defined to be, if I go back here, did I go too far? I went too far. SXX is this quantity here. So we take the sum of squared deviations of the xi's minus their average. So here's one formula for the estimator for B1. You can write it like this. So there's something out front, and then there's xi minus x bar times big yi. Remember that we're plugging in the random variable version when we talk about estimators. So if you think about what this function is, it's actually a linear function of the observations. What I mean by that is you could rewrite it like this as a sum I equals 1 to n of a coefficient ci times the random variable yi. So in this case, ci is just going to be xi minus x bar over sxx. Now this is important that it's a linear function because the normal distribution has this property. If you have capital Y1 to capital In, it's a collection of independent normals, then any linear function, or also called a linear combination of those random variables, also has a normal distribution. And the same thing holds for the big B0 hat. If you think about what this is a linear function of the yi's, and the average, sample average, is also a linear function of the yi. So this is also a linear function. One thing to remember about the normal distribution is that once you know that a random variable, say big B1 hat, has a normal distribution, there's only two additional things you need to know to completely specify that distribution. And those two things are the expected value of the normal distribution and the variance of the normal distribution. So to complete our analysis of the sampling distribution of big B1 hat and big B0 hat, now that we know that they're both normal, is to just calculate their expected value in the variance. So it turns out that they're both unbiased, and I'll leave this for you as an exercise to verify that they are unbiased. Turns out that the estimate of sigma hat squared, is also unbiased. This we'll have to wait till a little later on in the semester to learn why that's true. But for these ones, you can verify yourself. And the variance of these, which you can also verify yourself, is for big B1 hat, it's sigma squared over SXX. And the variance of B0 hat is sigma squared times 1 over n plus x bar squared over SXX. Now we said that big B1 hat and big B0 hat have a normal distribution. Sigma hat squared does not have a normal distribution. It has a chi-squared distribution. And again, I keep saying this, but when we study variances, we're going to come back and see why that's true. Now, we've said what the expected value of B1 hat and B0 hat are. We've said what their variances are. But what we haven't said is how they're related to one another. And it turns out that, while both B1 hat and B0 hat are normal, they're not independent of one another. And so one way of characterizing how two random variables depend on one another is to say something about what their covariance is. Now, this next calculation is going to result in a formula for the covariance between B0 hat and B1 hat. But we're going to come at this in a little bit of a roundabout way. So let me walk you through the argument here. So let's start with, what is the variance of y bar? So this is the sample average of the yi random variables, as I've indicated here in this equation. So because the yi's are independent, we know the formula for calculating the variance is you take the 1 over n out and square it. And because it's independent, you can bring the variance inside the sum. So this becomes 1 over n squared times sum variance yi. We know that the variance of yi is the same as the variance of epsilon I. So this becomes 1 over n times the sum of sigma squared. The sum of sigma squared from I equals 1 to n is just n times sigma squared. And so that n is going to cancel with one of the, this is a typo. This should be 1 over n squared sum sigma squared. So that n squared, which is supposed to be there, will cancel with the one of the n's in n sigma squared. And you get sigma squared over n. Okay, so that's our first piece of information. We already verified that above, but this is part of the derivation for getting the covariance between B0 hat and B1 hat. Now, we know that this formula is true. This comes out of the formula for big B0 hat. So if we go back to that formula, big B0 hat is capital Y bar minus big B1 hat x bar. So if we just rearrange things, we get Y bar equals B0 hat plus B1 hat x bar. So that's just this equation here. Now that we have an equation, we could take the variance of both sides. And since it's an equality, the variances have to be the same on both sides. So the variance of y bar is the same as the variance of B0 hat plus B1 hat x bar. Now, if we look at this equation, this is the variance of a sum. And there are rules for how you calculate the variance of the sum, and the rules work like this. You take the variance of the first thing plus twice the variance of, twice the covariance of the two things. So this would be twice covariance of b0 hat, b1 hat, x bar. So you should get x bar in here, but that can come out. So it becomes plus 2x bar covariance b0 hat, b1 hat. And then the variance of the last thing, which would be variance of b1 hat x bar, which is x bar squared variance b1 hat. And now you can begin to see what's the reason we're doing the derivation this way is because we get, in the middle of this equation, we get the thing that we want to calculate, which is the covariance between b0 hat and b1 hat. And then the rest of this derivation is just solving for this, because this has a known formula above, and this also has a known formula above. And we know that the whole thing is equal to sigma squared over n because it's the same as the variance of y bar. Okay, so I'll skip the details of the derivation. You can go through this yourself, but this is just solving that equation for the covariance. And I'll just say yada, yada, yada. You get that the covariance b0 hat and b1 hat is equal to minus x bar sigma squared over sxx. Now you can use the same sort of argument, and you can use these formulas as well to calculate the variance of the estimator of the fitted value. Okay, so just to recap here, this is also an additional piece of notation here. In practice, we don't know what sigma squared is, so we're going to have to plug in estimates of sigma squared. My notation here, when I plug in the estimate for sigma squared, sigma hat squared, into the formula for the variance of b1 hat, I'm just going to put a hat over the variance. So variance hat b1 hat is sigma hat squared over sxx. Variance hat b0 hat is sigma hat squared times the rest of the formula. Okay, we've come a long way here. We've talked about the simple linear model with one covariate. We've talked about how we get estimates for the parameters. And we've just worked out what the sampling distributions are for some of those estimators. There's a couple more things I want to cover before the end of this module. The first thing is hypothesis testing. So the way hypothesis testing works is you have something called a null hypothesis, H naught. So here I represent that as null hypothesis H naught is B1 equals B1 star. So what does that mean? On the left side of the equation, I have B1. Remember that B1 is our true value of the parameter under our statistical model. So this is a number, but we don't know what it is. And we're hypothesizing that it's equal to some specific value, B1 star. So often we'll say H naught B1 equals 0, or H naught B1 equals 1. 0 is the most common choice. And then here's how the logic works. We pick a statistic that I'll call capital T. We decide which values of the statistic constitute evidence against the null hypothesis. So for example, if we picked a null hypothesis B1 equals 0 here, and our statistic was the estimate of that parameter, so little b1 hat, then we would say we have evidence against the null hypothesis if the absolute value of b1 hat is large. So if the estimate is far away from the hypothesized value, then that constitutes evidence against the null hypothesis. We have to decide on a form of a decision rule. So again, following the same example, we would reject the null hypothesis. That's our decision is going to be reject or not reject. We reject if the absolute value of the statistic is bigger than some cutoff value C. So what this means is, say our cutoff is 10. I'm going to deem the null hypothesis to be false or implausible if the value of the statistic is bigger than 10 in absolute value. Then we use the sampling distribution of the statistic to create a specific decision rule that has probability of type 1 error equal to alpha. So instead of 10, I'm going to slide that number around and settle on a specific value such that the probability of rejecting the null hypothesis when it's true, which is a type 1 error, is equal to some small value alpha, which is usually something like 0.05 or 0.01 or 0.001. So in regression, for the slope parameter, a common statistic is to use in the numerator, b1 hat minus the hypothesized value, and you divide by the square root of the variance of the estimator. And here I'm plugging in a hat here. Now, this is all random variable, so I'm plugging in a random variable version of b1 hat, random variable version of sigma squared down here, and so this thing has a probability distribution. And it turns out that the probability distribution has a t-distribution with n minus 2 degrees of freedom. This is one of the things that we'll study later in the course of why it has a t-distribution. Our form of the decision rule is to reject if this thing is bigger than some cutoff. And it turns out if the cutoff I should pick so that the probability of rejecting when the null hypothesis is true is this number here. It's the t cutoff, n minus 2 degrees of freedom with probability 0.975. And this number is about 2. So this is all review for you. You've seen how hypothesis testing works. But to put this in the context of regression, here it is. Now, one thing to note is that the square root of the estimate of the variance is often called the standard error. So standard error is just a square root of a variance. So you've probably seen this formula before as big B1 hat minus B1 star divided by the standard error of big B1 hat. Okay, the last topic I want to cover is a confidence interval. Now, when you see someone talk about a confidence interval, in your head, what you should be thinking is that a confidence interval is a set of plausible values for the parameter. So if I say, here's a confidence interval for B1, it's from minus 0.5 to 2.0, then anything inside of that interval, like 1.2, is a plausible value for the parameter B1. What I mean by that is that we can't rule out that B1 1.2 is the true value of B1 based on the data that we've observed. So that's the heuristic definition. It's a set of plausible values for the parameter. Formally, the definition is the following. A 1 minus alpha confidence interval is a realization of a random interval that had probability 1 minus alpha of containing the true parameter regardless of the value of the parameter. Now that's a bit of a mouthful to handle, but and you could parse this definition, what it actually means, and we'll talk about it in the class. But I really, in your head, to keep the concept straight, I want you to think it's a set of plausible values, things that we can't rule out given the data that we've observed. Okay, so using that heuristic definition, we could come up with a method for generating a confidence interval. So I'm going to define A to be a confidence interval for B1. And so A is an interval. It has a lower bound and an upper bound that I'll call A sub L and A sub U. In the example I just stated, that would be, for example, minus 0.5 to 2.0. But when we're constructing the interval, we don't know what those are going to be beforehand. So let's leave them as variables here. And the way we're going to construct this confidence interval is we're going to do a whole bunch of hypothesis tests at level alpha. So you can imagine picking a really fine grid of values for hypothesized values for B1, call those B1 star. And I'm going to define the interval as follows. So B1 star is in the interval, meaning it's between the lower bound and the upper bound, if we fail to reject the hypothesis B1 equals B1 star at level alpha. And then conversely, B1 star is not in the interval if we reject it at level alpha. So this is kind of a constructive way of getting a confidence interval. We do a whole bunch of hypothesis tests, and we collect the values for which we fail to reject the null hypothesis. Now we can see that this method of generating a confidence interval conforms to our formal definition of the confidence interval. So here's how it works. The probability, we have to calculate this probability, the probability that the true value is in the confidence interval. All right, so B1 is in the confidence interval if the probability that we fail to reject H naught B1 equal to its true value. So why is this the right thing to calculate? We constructed the confidence interval so that a value of the parameter was in the interval if we fail to reject the null hypothesis at that value. So the event that B1, the true value, is in the interval is equal to the event that we fail to reject the hypothesized true value. Now, we can do 1 minus if we take the complement of this event. So this is 1 minus the probability that we reject the null hypothesis when it's true. And we've set up our hypothesis test so that this probability is alpha. And so we get 1 minus alpha. So if we look back to the formal definition of the confidence interval, it's a realization of a random interval that had probability 1 minus alpha of containing the true parameter, regardless of the value of the parameter. So this little calculation here verifies that this method for constructing a confidence interval is a valid method for constructing a confidence interval because it conforms to the definition of a confidence interval. And this is sort of a simple explanation of what's called the duality between hypothesis test and confidence interval. If you give me a hypothesis test, I can use it to construct a confidence interval, and vice versa. If you give me a confidence interval, there's a corresponding hypothesis test that can be used to generate that interval.